Welcome. As promised, I'm going to teach you how to graph linear inequalities, and it is not that hard. All you have to remember is what we talked about in the last video. Well, you do have to remember how to graph lines. So if that's something like, I don't remember, we have some videos on those a while back. Remember how to graph lines with intercept method and slope intercept method, and this stuff becomes very easy. The other thing that I was just referencing was the last video we talked about what a solution set to these guys is. It's not just a line. In fact, some of these don't even have the line as part of the solution set. But what we're talking about is an entire half plane, either the points above the line or the points below the line. All of them, entire half of a plane, is going to be a solution set here. The only way we can show that is by shading. By shading all the points in. Unless you want to list them all out, that would take the rest of your life and then some for all eternity, and you still wouldn't get to all of them because there's a lot of points, like an entire plane full of points, infinite number of points. So the best way we have to illustrate the solution set for linear equations was graphing a line that included all the points. That's what lines are. It's a way for us to say, what's the solution? These points, without having to write them. The same thing works for linear inequalities. We're going to show all the points that work by drawing a line and then representing whether the line is part of the solution set or not, and then shading the side of the half plane for which that represents the solution set, the points that are on the solution set. So here's how I want you to approach linear inequalities. Number one, look at them and immediately say, hey, that's going to be a shaded half plane, either the top half of the points in the universe on this plane or the bottom half. That's what's going on here. So we're approaching it by just thinking we're going to be shading here. That's what's going to happen. We talked about last video. Next, pretend it's a line. Pretend it is a line. Now, is the line going to be included or not? We'll talk about it. That's what this is going to give us in just a second. We'll talk about that. But pretend it is the line, because what's going to happen is that line separates your half plane no matter what. So that line is going to be the boundary line of your solution set. And we go, hey, the points above or below that are going to work. So the line that this is based on, it is important. It just may or may not be part of the solution set itself. That's okay though. We're going to pretend it's a line right now, and we're going to graph that line. So that's what I was saying earlier. You need the intercept method or the slope intercept method to graph quickly. I don't want to see plugging in points. That's crazy. It's going to take you forever, and there's a lot of problems. So that's number one. Now, how you graph the line is important. We referenced it last video. When you have a greater than and a less than, the line itself can't be part of the solution set. Think about that. If this is based on a line, x minus y equals 3, the points that actually do equal 3 are excluded from greater than. Greater than or equal to, yes, you would include that line, but not if it's a strict inequality like greater than or less than. It's saying the points that are actually on the line are no longer solutions. So how we show that, how we showed it for linear inequalities with one variable was parentheses. What that parentheses translates to is a dashed line. So a little dashed line says, hey, not part of the solution set. It's like a parentheses, a really long parentheses saying no, 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 no. None of those points are actually going to satisfy that. You can try it if you want to. Try a point like 3, 0. 3, 0, 3 for x, 0 for y, that equals 3. 3 is not greater than 3. That point, while on the line, would not be part of the solution set for this linear inequality. That's a big deal. So how we show that, in other words, just from here, from less than or greater than, use a dashed line. That's saying that the line itself is not part of the solution set. For less than or equal to, greater than or equal to, we use a solid line. So had we done that, that right there says yes, the points on the line. So basically, same solution set, that just includes the line in it. It says, yeah, all the points that are now on the line, those are also part of your solution set. It's very much like the bracket saying, up to and including that value. Now it's up to and including the points. That was just up to the points. So to show the difference, we used a dashed line for these guys. A dashed line if you're not including the line itself in your solution set. A solid line for these guys, saying, yeah, the line is part of it, and that's all the points that are on the line are included in that. So very much like parentheses or open circle, very much like bracket or closed circle. After that, once we do that, we're basically just going to have a dashed line or a solid line on your graph. Notice how that hasn't done anything. Even especially if you have a dashed line. If you just leave me a dashed line and go, yeah, we're done. What are you saying? You're telling me that you don't have a solution there? This is not my solution. That's silly. That's not what this is talking about. This is going to create a shaded half plane. So a shaded half plane represents our solution set. So once we have our line, we're going to test one point, just one. I'd like you to use 0, 0, and you can, as long as your line is not going through the origin. If it is, you'll have to use a different point, use like 0, 1, and I'll show you how to do that. But test one point. If you test one point in your inequality, it's either going to be true or it's going to be false. If it's true, so imagine you've shaded a line, or you have your line, and you test a point, and let's say that it's true. Well, then that point says, yeah, this one point is in the half plane that is the solution set. So if you have your line and you test a point and it says, yep, then that entire half plane is your solution set. That one point is part of all the points that work. All those points above there work. You test points all day long, and you would find that they would all be solution sets if you graph your line correct. Let's say that it's false. It says, oh, if this point that I test is false, then it's in the half plane that's not a solution set. All these points are all going to be false. That means that, well, let's see, if this is false and one half plane has to work, it's saying this one ain't it. This one would be it. The one down here would work. So you only need one point because either the half plane that the point is in is going to be the solution set, or the half plane that is opposite the point that you just tried is going to be the solution set. Let's try this with, we have about 6 examples. We're going to go through them fairly quickly because graphing is no longer the hard part. It's all about testing. So testing a point and finding the solution set, the half plane. So let's go for it. So I'm going to pretend that this is a line. Now I'm going quick because I'm taking for granted that you know how to graph lines from standard form really easily. So I'll be doing stuff like, hey, intercept method. This looks great for intercept method. All your variables are on one side, non-zero constant on the other side. I know if I cover up y equals 0, we get x equals 3. Remember, I'm pretending it's a line. I have nothing to do with the inequality right now at all. It does not come into play until you test your point. So it comes into play in how we graph our line, either dotted, dashed, or solid. So, but as far as our line, if I pretend this is a line, I get x equals 3. That gives me an x-intercept of 3, 0. Now, if I let x equal 0, y equals -3. That gives me a y-intercept of 0, -3. Notice one more thing, this is huge. Man, I have to have your full attention right now, so please focus on this. Don't miss this. What I'm not doing, man, I'm not freaking including inequality right here, okay? That's not what I'm doing. I am pretending it's a line. Now, I don't want you to go ahead, I don't want you to start replacing this with equals. I see a lot of students do that. Sometimes I teach it that way. I say, replace it with equals. That's pretending it's a line. But I run into trouble because a lot of students will then graph that and think they're done. Because they go, well, I should call it an equals, it's a line now. That's a problem. Or they will test a point into this and say, all the points are false. Well, obviously, if you test a point that's not on a line, in a line, yeah, they're all going to be false. That's why I don't want to start messing around with this inequality. If you need the equals to start doing this so it makes sense in your head, then okay, rewrite it. This would be you pretending that it's a line, and then all this stuff makes sense, and you get a line. Now, when we graph this line, you need to look at your inequality and determine whether you're supposed to use a dashed line or a solid line. Now, we talked about it a little bit, but that right there says none of the points on the line are included. The way we represent that graphically, and the graph is the only way we can actually show our solution here, is with a dashed line. So I have my x-intercept 3, 0. I have my y-intercept 0, -3. Looks pretty good. Using a solid line like that would say that the line is included in your solution set. It would say all the points are included. Now I want to show you why that's not true. Try a point like 3, 0. It's obviously on the line, But if you plug in 3, 0, you're going to get 3. 3 is not greater than 3. That's a problem. So, or 0, negative 3. 0 minus, excuse me, 0 minus negative 3, that's 0 plus 3. 3 is all still not bigger than 3. None of these points are going to work in that. The way we show it is to make it a dashed line saying no. So imagine you stop and go, I'm done. What have you shown me? Literally nothing. You're literally showing me here, this is not my solution. Good job. Well, yeah, that's a problem because you haven't given me anything right now. You just said this is the line that this is based on, but it's not a solution. That's where this comes in. That's where testing a point comes in. Now, I said it before, but it was probably a little vague because we hadn't had an example. I would love it if you test 0, 0 all the time. The only time you can't test it is if your line goes through it, because then it wouldn't tell you a proper half plane. So we're looking for half the points in the world. Either all the, look at my arm very carefully, it's a long line. Either all these points are going to work or all of these points are going to work. An entire half plane. So we test one point. So I'm going to put that point up here. I'm going to put check or test or something to reference that's what I'm doing. So test, maybe check because T I'll use for true. So I'm going to put check. If I check this, one big reason, I said it already, but one big reason I don't want a lot of people doing that from here, rewriting it is fine, but don't just change it and erase it, don't do that, is they'll check 0, 0 in this, and it will never be true. So if I check 0, 0, I want it checked in your inequality, not in an equation. That's a problem. So in the original inequality, I want to check there. So we check 0, 0. And it says 0 is greater than 3. Now, it's up to you. You got to determine whether that's a true statement or a false statement. So if I plug in 0, 0, it says 0 is more than 3. Man, that's false. I know that that's false. Completely untrue. So in my check, the point that I checked, that was a false statement. That point, here's what this says. This says that point is not in your solution set. Now, understanding that half the points on this plane are the solution set, it's telling you that's not one of them. In fact, that's in a half plane that consists of no points, which are solutions. So that's saying I'm in the half plane that's not the solution set. So if that's in the half plane that's not in the solution set, what's the half plane that is? The opposite one. So all these points over here, and this is how I'm going to shade it, all the points from here down are true. They will be true. We can try them if you want to. Try a point like 3, negative 1. If we put in 3, negative 1, that's 3 minus negative 1, that's 4. 4 is more than 3. Yes, you can try it all day long. In fact, that might be a great way for you to check your work. If you test one point and it's false, shade the other side, test a point over here. Just make sure it's actually true. That way you can determine if you've done it right, or at least have a better understanding of, yeah, I certainly have this down. That's the idea. Now, what if this had been true? If we had checked it and come up with a true statement, then we'd be shading this side, the top side. Because that true would say, hey, I'm in the solution set. Shade all this side that it's on. That's the idea. I hope that you understand it. I hope that you get this. I'll do a little recap. One big thing we can't do is just put a freaking line up there and go, hey, it's greater than, shade up. That doesn't work hardly at all. It rarely works, especially with negatives flying up there. So be careful on that. So here's the big idea. The big idea, one more time, is we're moving on beyond lines. Lines were a way to represent the solution to a linear equation in two variables. The lines were the solution that we got, were the solutions we got. Now with linear inequalities, we're beyond lines. We're saying, yeah, the line may or may not be part of that solution set, but either all the points above the line or all the points below the line are going to be in the solution set. It's called a half plane. The way we find it, we pretend that we've got a line, we graph the line like normal. The only difference is that if you have a less than or greater than, you're going to use a dashed line, signifying the points on the line are not really part of the solution set. Then we test one point. If that point is true, it's in the correct solution set. And so it's in the solution set. If the point is false, it's not in the solution set. The other points would be. You can always double check by testing a point that you've shaded and making sure that it works. So we're graphing and we're shading. It's not enough just to graph the line anymore. Now we got to test a point. That's actually what does it, isn't it? I mean, when you test a point, that's the only thing in the world that's actually using the inequality. That's it. We graph this as if it were a line. That didn't use an inequality. That was just putting points on a graph and saying, well, I mean, inequality a little bit, and that it's not included. But then testing the point actually used that and gave us a half plane. We're going to go a little bit quicker. I want to give you a lot of examples because some weird things start happening with some of these. Not a lot, but not a lot of weird things, but there's going to be more examples than I would normally give you. If you want to work ahead and do a couple of them, that's fine if you get this idea. But we'll do these three, and then I'll erase the board, put 3 quick ones up there when we get to go. Okay, so same idea. I'm going to pretend that this is a line. Right now I'm looking at this going, hey, that's going to be a half plane. So I'm going to have a half plane here, either shaded up or down. I don't know yet. We'll check a point for that in a little bit. Now, I'm going to pretend it's a line. When I pretend it's a line, I look at this and go, what's appropriate? Intercept method or slope-intercept method? Well, your variables are all on one side. Intercept method would work great. So, if I need to, I can rewrite this as equals, just to pretend. Please don't change that. I'm begging you, don't change that. This is just to get your line. We've already talked about that. This is how you get your half plane. Line, yes. Half plane, that's the one. This is what really we're trying to represent here is the inequality. Now, if you need to see the equals to be able to do this, that's fine. I know our x-intercept is at 4, 0. Let x equal 0. I know my y-intercept is 0, -1. We can graph really quickly with intercept method. I don't want you having to plug in points, so those methods are super nice because they let you graph lines quickly. Now, the next thing, we're about to graph a line. Now, the line is that separator that separates your half planes. We need to determine whether the line is included in the solution set or not. That's determined by looking at your inequality. So if you have the equals that's saying, yes, along with the half plane, all those points, you also include the line itself. How we show that graphically, much like a bracket, is with a solid line. So I'm going to graph this with a solid line, and what that says is that all the points on that line are also included in the solution set. I hope you're getting this. Your graph is the way that you show your solution. That's the only way we have to do it. All these points are part of it. There's an infinite number of points. You can't write them out. And in fact, you try it. Check it out. If I wanted to test some points on here, 4, 0, try 4, 0. 4 minus 0 is 4. Is 4 less than 4? No. But is 4 less than or equal to 4? Yes. Without this, the answer would be no. Then you'd have a dashed line saying, no, the line's not part of that. With the equals, yes, the line is part of that solution set. That's why we show solid versus dashed, what we did on erasure already. Next up, imagine you just gave me that and left it. Your teacher's not going to be very happy with you because if you give me this for this, it shows your instructor or it kind of signifies that you really don't understand that there's a difference between these two things. Because if you graph this and give me this, you've really just graphed that. That's a problem. So your inequality needs to represent a lot more points than that. It's got to be an entire half plane. 0, 0 is a great point to check as long as it's not on the line. So I'm going to check 0, 0. I always write it out. I don't do it in my head. It's too easy for me to make mistakes. So if I check 0, 0, it's always in the original. You probably understand why we use 0, 0. It makes everything 0 on one side in standard form. It's awesome. Now we get 0 is less than or equal to 4. We think about it real careful, make sure we got this. Is 0 less than 4? Yeah, for sure, that's true. So we checked 0, 0, and it was true. Here's what this is saying. So the entire recap, here's what this is saying. This is based on a line, graph your line. Use solid for equals, use dashed if you don't have the equals. That says the line's part of it or not part of it. Then we test a point. This point right here is not on the line. It's in one of the half planes and says that point right there was true. Well, what that says is that, hey, I'm part of the solution set. In fact, all of us over here, all these points, we're all going to be true. The solution set is this entire half plane. And you can test another one if you'd like to. Test all of these points. They're all going to be true. If you want to double check, test a point like 2, -2, something in the other half plane. It should be false. 2 minus -8. 4 times -2 is -8. So 2 that's like 10. Yeah, that's not less than 4. So I know that these points are false. Those are true. We have to shade a half plane to represent a solution for linear inequalities in two variables. It's all about the graphing. That's the way that we show our solution. Now, next one, if you want to jump ahead and do that one, that'd be a good idea. I'm going to erase this one. Starting to notice that the graphing is not the hard part anymore. Actually, none of it's really super difficult, but the graphing is kind of the easy part. The hard part is understanding the half planes, getting the interpretation correct. So I'm going to pretend it's a line. All these linear inequalities in two variables are based on lines, but that line is now the separator of our solution set, of our half plane. If we let y equals 0, then x equals 4, and we give an x-intercept really quickly of 4, 0. That's what the intercept method is used for, is finding x-intercept, y-intercept. It works when your variables are on one side and you have a non-zero constant on the other. If we let x equals 0, then we get a y-intercept of 0, 6. That's pretty fast too. How would you graph that line? Would you graph it with a solid line or with a dashed line? Because we need to know that at this point. With inequalities that have an equals, we're stating, and you need to understand what we're doing. With the equals, we're saying, hey, that equals, that is the line. If we have the equals, it's saying the line is part of our solution set. We show that with a solid line. Now lastly, in order to say what the solution set is for an inequality, you need a half plane here. We need to shade something. So we're going to test one point. The easiest point to check is 0, 0. Use it every time unless your line goes through the origin. Naturally, we're trying to see what the points that are not on the line are doing. Well, if we test a point on the line, it's either going to say true or false depending on whether they have equals or not. That's a problem. It wouldn't tell us what side of the line is also part of the solution set. That's why we test a point that's not on the line. 0, 0 is not on any line unless it goes through the origin. So we'll check 0, 0. If we check that in our original inequality, it says that 0 is more than 12. Man, that's clearly false. 0 is not more than 12. So we checked 0, 0. That's right here. It was false. What that's telling you, this guy's like screaming at you. No, don't shade me, please. I'm begging you, don't shade me. Don't shade me because I'm wrong. I was a false statement. I don't want to shade false statements. False statements are non-solutions. We saw that last video when we tested those points. It was false. It was a non-solution. That point is not a solution to that inequality. In fact, it's saying all the points in this entire half plane are also not solutions. Well, that means that the points here aren't solutions. The points here are solutions. It's saying this side of the half plane is not your solution set. One side of the half plane has to be your solution set. Therefore, it's this half plane. And you can test a point like 4, 1, and see if it's true. 4 for x, that's 12. 1 for y, that's 14, that's more than 12. on that side, so I know that that's a true statement. That way we can be certain that we have the correct shading, provided you graph your line correct. Now, that says something. We're going to want to be really good at graphing lines. So imagine this. Imagine that you messed this up and got -6. Well, your line's going to be completely different. Your shading's not going to look remotely near what it should be. You'd have a completely different half plane that you'd say, all these points work. And you'd be very confused because when you started testing points in there, some would work and some wouldn't. That'd be an issue. This is also based on graphing linear equations, sure, because that equation is what's separating your half plane. We've got to get that right to get our half plane correct. So we're going to try 3 more, some kind of weirder ones, not necessarily harder, but I want to show you what else can happen here. Okay, let's try these. So firstly, we have all of our linear inequalities. That one looks kind of strange. We'll talk about that in a minute. We have all our variables on one side, non-zero constant on the right. That's set up for intercept method. We have all our variables on the left. That's a problem. We'll talk about that one. And then we have without a variable. So these are some weird examples. We'll talk through exactly what these things mean, exactly how to go through them. Now, if we're going to solve these, maybe the first thing you look at is what we should be getting. If we have inequalities, we should have a half plane and a half plane and a half plane. We will be shading here. Next, what type of line would you be using? Solid or dashed for each one of these? Well, let's look at our inequalities. That's got to be, it's got to be solid. Dashed, dashed, signifying the line is part of the solution set here and not part of the solution sets there. So let's graph our lines. We know that all of our linear inequalities are based on lines, so we'll graph them all. And then we'll determine the half plane that represents the solution set for an inequality. Okay, so number one thing, let's pretend that these are lines. So I'm going to pretend that's a line. We're going to write out equals 4 if you want to. Just don't erase that. Remember that when you're checking, you're always going back to this statement. So if I let y equals 0, we get 3x equals 4. Remember that this still works with fractions. If you write the fraction correct, this still works with fractions. If we let x equal 0, we get 0, -4. As our y-intercept, we have 4/3 0 as our y-intercept. I'm sorry, x-intercept. So we know our intercepts. Now, some people might not like the fraction here, so this is why this is in kind of the weird category. I just need to mention something to you. If you are going to solve this for y, if you're going to do that, you absolutely must be cognizant of the fact that when you divide by a negative, your inequality must flip over still. So if you're going to do it, and subtract 3x, which is perfectly fine. When you divide by the negative and you do it everywhere, you get positive 3x and -4. That inequality must reverse itself. Otherwise, your line just ain't going to look right. All right. Well, your line will be fine, but your half plane will be completely wrong. So be careful of doing that, please. I'm going to leave that so you can see a different interpretation just a minute. It's kind of cool. So let's see. I know 4/3, it's 1 1/3, 0. -4, we've already determined this is going to be a solid line, so let's graph this with a solid line. And then we check 1 point. We can still check 0, 0. I'm going to put that on there. I'm going to put check. But we check it in the original inequality. This is saying that 0 is more than 4. I'm not so sure about that one. That looks false to me. So that says we checked 1 point not aligned. It says I'm in the non-working half plane. That means the other half plane must contain all the true points, all the solutions set. So the half plane is yes, including the line because of the equals. It says take the line with it and all the points, we'll say below to the right in this case, but all the points in this particular half plane. Now, I told you this was relevant. This is kind of interesting. Notice, can you still get the same line? Of course, here's -4, here's up 3/1. I don't have time to reteach you graphing because that slope-intercept form is in graphing. Now, what's also interesting is that this kind of plays into it, the solving for y. A lot of people like this because it will show you where to graph properly. Do you remember that if your variable was on the left-hand side, it would show you the direction to graph on a number line? If it was this, you graph left. This, you graph right, which is very convenient. The same thing works if you have solved for y. Let me show you. Here's y positive and here's y negative. This says down. Graph below that line. And it works. If you have solved for y, that arrow just kind of go like this. That way. Graph below the line to the left or below. So that arrow still actually points to the side of the line that you're graphing. That's kind of neat. But you have to have a solve for y. You can't do it from here. It won't work. But if you solve for y and you follow the rules that you should be following, then that'll show you what side of the line to actually shade. Just turn your head to the left and go, okay, well, if it had been greater than, we'd shade above, less than, we shade below. So it'll show you that as well. If that makes sense, cool. If not, don't worry about it so much. I'll show you one more time over here. So let's get to that one. Hope this makes sense. We need the line, solid line, test 1 point, shade the side of the line that is true. Now, intercept method is awesome when it actually works. But in order for intercept method to work, you have to have a non-zero constant. That's not it. That's a problem. Because if you pretend this was a line plugged in y equals 0, you get 0. That's a point 0, 0. If you pretend x equals 0, you get 0. That's the same point 0, 0. You can't graph a line with the same point twice. That just say you're going through the origin. We're just going through the origin. That's what that 0 actually says. So whenever you get this, whenever you get something that doesn't work for intercept method, either it's solved for y already, I kind of solved that one for y, or you have a 0 constant, don't use the intercept method. Use slope intercept method. Solve for y. Now notice, I don't have to reverse that inequality. I'm not dividing by a negative. This is perfect. This has a y-intercept of 0, something we already knew, and then it has a slope of 3/1. If you still want to pretend that this is a line, just so you can graph it, if you need that, that's okay. But remember, this is based on this line. This is not just this line. It's just to help us see the separator of our half planes, the boundary. So, y-intercept, 0. In fact, that's exactly what we found because the intercept method didn't work. We would have an intercept at the origin. Our slope is 3/1, says positive 3, right 1. We're going to graph this with what type of line? What do we got here? Well, it doesn't have equals, it's saying the line's not part of the solution set. So we got a dashed line saying, nope, not part of it. And one more thing. We have tested the point 0, 0 the entire time because it was not on the line. If your intercept method doesn't work, or if you just use slope intercept method and you go through the origin, or if you go through the origin anytime, you can't use 0, 0 because it's not going to tell you a half plane. It's going to say, hey, 0, 0 doesn't work. Great. What side of the line is it on? It's on the line. Oops. Because it wouldn't tell you true or false. You need something true or false as being on one side of the line or the other. So we need another point. Now me personally, I always use 0, 0, and if I go through the origin, I use 0, 1. I've created a pattern that's what I do because I know that's my fallback point. So I'll check 0, 1. So when we check 0, 1, just remember we're putting 0 for x, we're putting 1 for y. Don't reverse that. Don't do 1 for x, 0 for y accidentally. We're doing 0 for x, and we're doing 1 for y. Is 1 less than 0? No, clearly not. So that's a false statement. So I checked 0, 1. I showed where it was because that's important. I want to know where my point is and I'm checking. It's going to put it in a half plane. I know that that is false. I know that point does not work. That's a false statement. 1's not less than 0. So this entire half plane is false. If this entire half plane is false, the other half plane is true. Now, I said one last thing. It might not have made a whole lot of sense to you, but if you have in slope-intercept form, it will also tell you what side of this line to graph on. This says my variable's on the left-hand side. If I look like this, that arrow's pointing down. So that would be below the line. This would have been above the line. If all else fails, test a point. That's probably the best way to go, but I am showing you that there's another method here. So no matter what you do, it says this half plane don't work, this half plane does work. That's the idea. Graphing lines with dashed or with solid, representing the inequalities properly, and then testing a point. If we test the point, shade the side that's true. Now we come to some weird ones. If you remember this, when we graphed these linear equations, we got to vertical and horizontal lines. Well, wait a minute. If this is based on a line, then it's based on that line. It's based on x equals 3. Oh, now what is it? What is that? Is it vertical or is it horizontal? Remember that when we're missing a variable, we're missing that particular intercept. If we're missing a y variable, we're missing a y intercept. The only way that we can be missing a y-intercept is to have a vertical line. That's a vertical line through x equals 3. Is it a dashed vertical line or a solid vertical line? Well, it's not that one. It's dashed. Now, we still have to represent a half plane, but it's even easier. It looks weird, but it's even easier. So what half plane would you want to represent? The side to the left or the side to the right? Do you remember? Oh man, I prefaced it right here. Do you remember that if your variable's on the left-hand side, that it points to the side that you should shade? Now you can still test 0, 0, but there's nowhere to put the 0 for the y. That's okay. If you tested 0, 0 here, you'd have 0 for x. No place for y. Who cares? So 0 for x, 0 is less than 3. That's true. That would be true. It says this half plane is what you shade. Look at the variable. It's on the left-hand side. It's organized for us. Shade to the left. Either way, you're shading this side. Now maybe this will make a little bit more sense. Like if you turn this way, you'd shade below. Weird. Let's do one more because I want to make sure that I hammer this home. What if this weren't x equals 3? What if this were y is greater than or equal to negative 3? with y equals, if this is based on line, this is based on y equals -3. So our line would be a horizontal line. It would be solid. I hope you know why. And we'd still test a point. So if we test a point, well, you can test 0, 0, but there's no place for x. That's fine. So test 0, 0. It says 0 is greater than -3. Yes. Yes, 0 is greater than -3. We will be shading this half plane. But notice how your variable's on the left-hand side. It's pointing, well, if you look like this, that would be pointing up toward the positive of the y. It still shows you what side of the half plane that you're supposed to graph. So it's kind of interesting. There's some major parallels between linear equations in one variable and linear equations in two variables. There's also major parallels between linear inequalities in one variable and linear inequalities in two. If you have them set up correctly, it will show you, just by its direction of your inequality, what side of the line to shade. If not, if you forget all of that, doesn't matter. Just plug in a point. Plug in a point like 0, 0. It's going to be true here. Shade the side that 0, 0 is on. Shade the true side. If it's false, that's not the true side. I really hope that you're getting this, that you're understanding it. Next time, what we're going to do is we're going to put these ideas together, and we will be graphing systems of linear inequalities. Is it hard? No. Think about it. If you can graph one of them, and you can graph another one, can you do it on the same set of axes? The answer is yeah, it's not even that hard. We'll talk about it next time.